We're going to talk about Stone Cold Steve Austin's favorite law, the Beer-Lambert law. I can't even talk like Stone Cold. It's terrible. If you don't know who Stone Cold is, shame on you. All right, so when we're looking at spectroscopy, we're studying electromagnetic radiation that's emitted or absorbed by chemical species. It's like different solutions, you could say. So if light is shown through a solution of an unknown concentration, so depending on the amount of absorbance can be used, we can use that to determine the calculate the concentration of the solution. So we can use the absorbance to calculate concentration. So these two have a direct relationship. The more concentrated a solution is, the less light that can pass through. So like looking at this one right here, less light can pass through here, but more light can pass through here because it's not concentrated as much. It's dilute, so more light can pass through. And again, we can use molarity as a conversion factor in these problems that we're going to do. So like, for example, if you have 2 liters of a 0.25 molar solution, how many moles are there? Again, you just multiply the two together and you get your moles. So again, we can use molarity as a conversion factor. All right, so different colors show different colored solutions absorb different colors. So you want to use the color wheel to kind of figure out what wavelength you should use to complement the solution that you have. So a real easy way to remember the color wheel or what's complementary. You have red and green, Christmas, yellow and purple, Los Angeles Lakers, terrible. And then you have blue and orange, Denver Broncos. Hey. All right, so this is the process. So this is a lot, so I just left it typed out for you. So we're going to use a spectrophotometer or colorimeter. We have a colorimeter, this Go Direct one in this slide right here. That's what we have. We will do this lab, but not in this unit. We'll probably do it a little later for time and because I may not be here. All right, so again, when we're looking at absorbing light, electrons in the ground state absorb energy to go to the excited state and move up higher and then release energy, which is the photon. And so that's how transition metals have different colors, because the transition metals absorb photons that are in the visible portion of the spectrum. Hence why we have these transition metals have these pretty colors. So this colorimeter, it consists of a light source and a diffraction gradient that separates the light into different wavelengths, like in here. So it's going to pass through a cuvette. So this is our cuvette right here. That's going to hold our sample, and the light will pass through it, and it'll tell us the absorbance. So you always want to use a blank sample to calibrate your colorimeter or spectrophotometer. Say that 8 times fast. So when you put a blank sample in there, it'll set your absorbance value to 0, and that's what you use to compare. So this is equivalent to like tearing the scale. Like you always want to set it to 0 before you put something on it. Or if you put a weigh boat, put the weigh boat on the scale, press 0. This is equivalent to that. So you always clean the cuvette with a lint-free tissue, which we have. And you never want to use your fingers. So this person right here is breaking the rule, because now his fingerprints are all over it. And when that happens, it's going to mess up your data and you're going to get this. So you never want to touch it with your fingerprints, because it can interfere with the scattering of light and reaching the detector, and you'll get data that's skewed like this. So you don't want to do that. All right, so then once you add your cuvette to the colorimeter, you'll get your data, and then again, the more concentrated solution is, the more light that is absorbed by the solution. And it's not going to pass through. So then we can use this Beer-Lambert's law to describe this relationship. So A is absorbance. It never has a unit. So here's absorbance. So you'll see this as little a or an E. That's your molar absorptivity. That's just how intense a sample absorbs light, which is measured in inverse molar times inverse centimeters. And then B is your distance traveled by the light. So that's always going to be 1 centimeter. This is standard for all cuvettes. So always assume 1 unless told otherwise in the question. So if it doesn't give you the information, it's 1. And then C is concentration, which is molarity. So then finally, once you get your information, your graph should look like this. And you'll get your absorbance. And again, the standard path is always 1 centimeter. All right, so this is an example of what a problem will look like. So you have a 0.389 gram sample of an ore. It's completely dissolved in nitric acid. The mixture's diluted with water to a final volume of 25 milliliters. Assume that cobalt ore sample is converted to the cobalt ions. So first, we're going to look for the concentration of the cobalt ion in the solution. And so if the absorbance of the sample is 0.45, we're going to go to 0.45 and go all the way over here. So I kind of have it drawn out. Oh, it's uneven. Okay, so it's not where it's supposed to be. So you go to 0.45 and your concentration should be right about here. So 0.080 is our concentration of the cobalt ion. So now we got to calculate the number of moles of the cobalt ion in the solution. So again, this was our concentration of the cobalt ion based on the absorbance value given to us. So all we got to do is find the number of moles by just doing our molarity concentration calculation. Moles equals moles over liters. So then X should be 0.002 moles. All right, now going back to unit 1, calculate the mass percent of cobalt in the 0.389 gram sample of the ore. So again, this is our total mass. So that's going to be on the bottom. So we have the moles of our cobalt ion. We got to multiply by the molar mass. And then we'll get our mass of the cobalt in the sample. So now you just divide by the total mass of the sample, multiply by 100%. So you have 30.3% of cobalt in your sample of the ore. That's it. We are done. All right, so same thing as last class. We'll have a starter with all the 3 of these units, and we'll just practice with this. So if you got questions, shoot me an email.